Okay, we're live. We are starting again. I was informed that we stopped on slide 29, so I'm going to go to number 29. This is still lecture 1, actually. And how do we like the new class start time? We like it. I like it. I didn't have to sit around for an hour twiddling my fingers, thumbs, or whatever. Okay, so I talked about permissions. Are you serious?
Yes.
All right. We looked at the change mod. Did we look at change mod? Wow. Did we look at listing out the files to see the permissions? Yes? Okay, good. If you say so. We looked at change, the change owner. Hey, we got to keep it down in the back. Yoo-hoo, we're starting. We are officially starting class. Thank you. Okay, so we looked at change owners as well. Okay. All about me, who am I, and password. Changing your password. Okay. What everybody else is up to? Maybe, perhaps. Yeah, actually, I remember that. Yeah, we did uptime. How long has the server been up? How long has the system been up? Working with programs, processes, and multi-thread. This is why people like Unix. It's a multi-threaded, multi-processing type of system where we have multiple processes running simultaneously, and we have a process order, and we have a hierarchy of processes that all start with the kernel that I'm going to talk about today in lecture number 2, as soon as we get there. But it all breaks down to being able to identify, for our introductory purposes for right now, every process that gets started has an ID that starts with 0, actually, and works upward. So the higher level processes are assigned to user level. There's too much noise in the back. Yoo-hoo. You can take it outside. There's plenty of room out in the hallway. All right, thank you. It's still kind of loud in here, isn't it? I'll just stop until, okay, there we go. Until it quiets down. Wait a minute, she stopped talking. Okay. Okay, I'm back. All right, so if we'd use the command PS, it will display the processes that are currently running on the system. We can actually kill processes. We can start processes in the background. We can run processes in the foreground. And we can multitask in terms of the programs that we're running. Most of you are familiar with Windows in a Microsoft environment, and even on this MacBook, you double-click on an icon, it opens up a program. In Linux, Unix is the same thing, except for unless you're using the Sun Windows or a desktop of some sort, like GROM or KDE or something, you're not really double-clicking on icons. Instead, you're running commands. So when you do that, you're starting a new process. So in a Linux and Unix environment, you can have a lot more user-level process control. It's kind of equivalent to the Windows Task Manager. When you press Control Alternate Delete, you bring up a Task Manager. It shows you're running processes on the system. And in terms of what we're looking at here, if we run PS, and sometimes the command is called jobs. Here, let me clear this out. PS gives us our running processes, which we don't really have very much running. I don't have very much running on this. Or if I type in jobs, it's not support. Actually, it is supported. I don't have any jobs running. So jobs are another name, but it's a higher level of abstraction. It's a utility that's built in that gives us more information about the processes. It's the same concept, however. And if we want to kill a process, well, actually, if we want to put a process in the background, we use an ampersand. So if I said, ampersand ls, ls ampersand, dyslexic today. It actually it put the feedback. It's actually running in the background, but an ls is just going to end real quickly because I'm just listing out the directory content. If I started a script, or if I started a process, if I wanted to put it in the background, which means it's not using my foreground memory, not using my foreground I/O, then if I typed in PS, actually, because I put it in the background, it stopped on its own because of the ls didn't really do anything. But if I typed in PS, I would see the process number of that background process. And if I wanted to, I could type in kill space the process number. I wonder what would happen if I typed in 397, actually. Did it kill it? Huh? No, didn't kill it. For a protected process. I tried to kill my bash shell. I couldn't kill it. Kill all now. There's a kill now, 397. Oh, Kill, invalid signal. Not supported. Nope, 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 no, no, nope, not supported. Alright, long story short, there's a way of not waiting. There's a way of getting it to kill now, to kill all processes now. And you do that essentially if you want to shut the system down and you're the system administrator. You've got multiple people out there working on these Unix terminals. They're all logged in through remote connections, local connections, and you have processes running. It's kind of like turning your computer off while it's got a bunch of stuff loaded. You might corrupt files. You might not have any data that's being saved. So if you run a kill now or kill all or shut down now, which actually runs a kill all on running processes, you end up gracefully shutting down every one of the programs that happens to be running so that you can reboot the system, something of that nature, which is why, or which is one of the reasons why the kill is actually kind of popular for system administrators. And another reason why it's kind of popular to know what processes are running, because then you know, not only can you tell who's logged in, how long the server's been up, what processes are running, you can kind of like do a load balance and see, well, what users have the most processes loaded? Because the process information is going to tell you what user actually started the process and when, how long has it been running. So you can kind of judge as a system administrator, you know, manage your users a little bit more efficiently and say, well, this person's been downloading DVD movies all afternoon and has 12 different processes open for this program, for this download stuff, and let's kill all that stuff. And then the user would essentially be sent a warning or something like that, maybe by the system administrator. So if you're abusing the company resources, you shouldn't be downloading or something. So it's a way of monitoring. In fact, it's a way of just checking to see what the system load is all about in terms of being able to load balance it. So those commands, the PS and the kill, come in handy, and the kill takes off the process ID, which essentially terminates the process. So only you and the super user of the root has permission to kill processes that you own. Other users can't kill your processes, which is why you set up an elaborate, user system where you have different levels of privileges, and you can say, well, this user has root privileges, which means you have access to the root directory or root drive outside of your home directory, or this user has admin privileges or something. The higher level of privileges, the more dangerous you make the user. So you usually want to put everybody at user level and don't give them very much so they can't destroy everything. So advanced program options, essentially running a command with options and then the ampersand, as I mentioned before, that ampersand symbol. I don't know why I always like to put it before, but it goes after. So after the command. Runs it in the background, and then it prompts returns immediately. Well, in my case, it didn't actually when I tested it out, only because it terminated before it would actually give me the prompt, so because I ran an LS. You can match zeros or more character wildcards using the asterisk. Same thing you have in the DOS environment from Windows, you know, copy star.star or something, or rename or delete star.star, kind of dangerous commands. I copy everything from a destination using the asterisk and then a destination. So obviously you can get into trouble with those particular asterisks. Editing files. In the old days when you learned Linux, in the old days, Unix and Linux, they used to teach you VI. You took a whole course and half of what you were doing is learning VI for some strange reason. I'm not quite sure why, or Emacs. Those are the original, extremely hard to use text editors. And I believe I showed you Nano perhaps last time. If not, I can show you Nano right now, and it's probably the one I would prefer using. And why do you need a text editor? Because what you're doing in Unix, running commands and writing commands. The writing commands is done essentially by creating a script. You want to save it, so you save it in a file. And everything on the system is essentially a file. So you run the file, you change the properties using a change mod command, make it an executable file. And you can create a batch file, or you can create a script file that's going to execute commands for you, to run a backup, to search for something, to do some sort of utility. So Unix programmers, Unix users, administrators need text editors. Everything's written in a text editor, which is why in a lot of classes you end up spending a lot of time learning VI, which is supported in native everything. But also Nano or Pico. I like Nano. The original was Pico or Pine, which is used for email messaging. In fact, you have email. In fact, I can send an email message from my terminal prompt on my MacBook, actually, which is kind of the long way of doing something. I'd rather open up an email client and have a graphical user interface to do that. But everything you can do through the GUI, you can actually do manually through commands. So having a, I'm not going to show you because I think I showed it to you last time, having a text editor at your disposal, it's not a bad idea when you're writing text files. But as we start looking at scripts, I'll bring up Nano and I'll demo that for you. Let's talk about input and output. This is where C programmers struggle in the first couple weeks of class because they learn stdio.h, which is the C equivalent to standard in, standard out, standard error. And all three of them are supported by that library. Because C, Unix is written in C. C and Unix are pretty much the same thing. Yeah? So we have to think about output. Standard output is usually defined by your mapping. So I'm sitting at a terminal. And that output window that I'm sitting at may not necessarily be my standard default output. It might be another terminal window. Which is the interesting thing is we might have like 15 different people logged in to one station. And they might have all different outputs. And the outputs can be going to different directions or they could be saved to files. And we have this thing called direction and redirection that exists in Unix where we can pipe, we can filter, we can direct input, output from all different sorts of locations. So it's not like the old Windows version where you set out a Windows box, work at a Windows box, and there's your I/O right there. Linux is you can redefine the environment for yourself. So you can log in on a terminal window, and your terminal window is your default output. And the errors can go to a certain directory or a certain area in which maybe an admin can monitor the errors. So we all kind of understand the concept, I believe, of input and output. And anyone who's ever done any programming understands input and output. But it is definitely a low-level Unix terminology, Unix term. So program commands contain input and output. They're streams. It's referred to as a stream, actually, in the Unix environment. So often stream-based, and there's no buffer normally either. So programs also have error output that can be caught and used. So standard input, standard error, standard output are pretty much the terminology that's being used to classify those different types of things that are going on. When you learned C++, you looked at the directional operators, which were redirectional operators. When you did C in and C out, if you were familiar with those programming language concepts from iostream.h, you had a higher level library that mimicked what Unix actually does in terms of the output and the direction. So oftentimes you want to save the output, standard output from a program or a file. It can be done with a redirection operator. And is just as it shows here in the slide. I'm going to run ls and I'm going to send, let's say, the output to a file and I'm going to call it my file. So this symbol used as a command prompt redirects your input and your output. Because you can take input from something, send it to somewhere else. And that's what gives Unix actually kind of a nice flair to it in terms of utility. So you can redirect the output from my program to my file. Similarly, you can append the output of a file instead of rewriting it by using the double arrows. So this is actually a concept where that C in and C out from C++ is coming from. And just to kind of give you an example of the power as an example, if I were out here and I did an ls, right, minus L, let's just do that. And I wanted to send it to a file and then call it my file. Hopefully my file doesn't exist. Nothing happens. If I were normally to do an ls minus L, stuff would be printed. It's just going to be a list of directory files that I have here. But because I send it to my file, let's do nano. If I type in nano space my file, is it my file? There it is. There's the output. It automatically got saved to a file. Try doing that in DOS. It doesn't work because we don't have that concept of redirection. Similarly, I could take input from something, send it to a program, and I can string the directional arrows to say, take this input and send it to that file, send it to that file, send it to that file. Which means you can take input or output from something, or output from one program, send it as input into another program. And then basically create some pretty unique utilities. And this is essentially what a lot of scripting languages are doing. A lot of scripts are taking and finding out how many people are currently logged in, and then for those people who are currently logged in, finding out, well, how many of them are using this server, And then of those people who are using the server, what jobs are they running? What programs are they have opened up? And for those people who have got those programs opened up, you know, how long have they been opened up? And you can actually kind of like further analyze deeper and deeper and deeper using the same input that came out of some search you did. And nano is if I just type in nano, I can create a file. Actually, I said I was going to save, but it's a GNU text editor. So if I do Control X. The reason why I like nano is because it has this little menu on the bottom of the screen here. So if I pressed in Control X, it's going to save. For VI, you have to memorize a bunch of commands. You have to, there's no menu that shows. In fact, I don't even want to bring VI up because I have to go into the escape sequences to exit out, and I don't remember all the commands. But VI is one of those editors where you actually have to memorize commands. Nano gives you a menu, so you can remember. All right, so that was a kind of a way of taking an LS and sending it to a file. You could take the file and do something with it. Here's another example of doing the opposite for the input, using a cat as an example. To concatenate something. So input can also be given to a command from inside of a file, or from a file by typing it to the screen. So it would be maybe impractical to retype everything. So you could say, cat program input, and then you notice that the direction of the arrow changes. So the output, it's going out, kind of like a blowhorn. You're kind of yelling out. And here's the input is the opposite, where you're taking it in and it's going to the narrowing point, which is going to be the command that you're going to send it to. So this command takes a series of commands for cats, which prints a file to the screen. So program input is printed to standard output, which is a directional command for my command. So we'll see piping in a few minutes, where we can run something and then run it inside of something and then send this input and redirect it to this output to create this output. And it makes for some really powerful commands, actually. So performing a normal redirection will not redirect standard error. Standard error always goes to a certain area, but we can redirect it. So in Bash, you can accomplish this with command 2. In fact, we have numbers on standard input, standard output in arrow. It's 0, 1, 2. So we can actually, instead of referring to it as standard input, because we can use it as an environment variable and say stdin, std out, and then error, or we can go 0, 1, 2, and then we can refer to it by number. We're shortcutting, where it's just an abbreviation for standard input, standard output, or standard error. And we can say take the standard error and send it to file 1, which is 2, the directional to file 1, which is we're going to redirect all of our standard error to file 1. Because what if we're troubleshooting some stuff, and we want to know, we're supposed to have some file located somewhere, and it's a log file, and we're supposed to read the file and log it, and we're supposed to do something to it, but the file's not there. So it comes back with a file not found error or something, and then we can redirect it, let's say, to standard IO, and it would actually show up on the screen and say, hey, no, file not there. Because if you notice, when I type in ls, nothing happens. When I typed ls and redirect it, the command worked. But if I had an error message, it's not going to show up on the screen. It would show up in an error log. It would show up on wherever the standard error was supposed to go to. So you can merge the standard error with the standard output. Most popular is to say 2 with this directional to background and 1. So essentially what you're doing is you're merging the two. So standard error now becomes standard output. So if you get a file not found error, it actually shows up on the screen instead of like in a error directory. Sometimes the errors actually, by default, standard error goes to a file. It's always redirected to a file, and they're usually a log file, user errors. You can actually take that and kind of troubleshoot it a little bit and say, well, user hacker is trying to run this program, but the program doesn't exist, or it's not mapped to it correctly. And you can look at the file, the error file, and you can go, oh, look at that, she tried it 12 times, and it didn't work, all 12 times. This is the error that's generated. You can kind of micromanage things. Okay, so I mentioned it already, but here's your formal definition of it. It's called a pipe. So we have pipes. It's like a plumbing pipe. No, it is kind of like a plumbing pipe if you think about it. You use a pipe operator, and that is the up and down line, which is kind of interesting. You'll see it in a lot of commands. One of your assignments will have you pipe a lot of stuff. So you can link things together. You can link commands together. So the pipe will link the standard output from one command to the standard input to another. which is kind of like how a pipe works. If you think about it, it carries water throughout a system. So when you pipe it together, you're just connecting it. So the water flows in here and it continues flowing this way. So you string commands together and you pipe them with a line between connecting the commands. So you can run like 5 commands all at one time and have them all work together. And then people get way too overzealous with how many commands are, and it's like a contest to see how difficult you can make the command sequence. how many things you can pipe in there. Very helpful for searching files, because you can search inside of a file and then inside of that file and then inside of that file, as I mentioned before, trying to find something inside of something. Which brings up the concept of search. And one of your assignments, if you haven't looked at them yet, are going to have you to run some greps as well, and with some pipes. And some of them are actually quite challenging. So you can run all of them on your MacBook, or you can run them on a CD boot up disk. So majority of the activity of the Unix system also involves searching for files and information. If you think about it on the Windows system, you got icons everywhere. You just look for the icon and you double click on it. In Linux, Unix, you got it all over the place. And you got a command prompt you're looking at. So you got to grep a lot, or find. Actually, there's a find and there's also a where is command, where you can actually locate these executable files, or locate what it is you're looking for. So find is a utility to find files. Grep is the best utility ever written in Unix, well, according to the slide. Searches patterns inside of files and will return the line if it's found. So assuming we're looking at a text file, inside of the file, it's kind of like what Microsoft's find does in the search utility, search and find, where to look for passages inside of files and tell you, oh, this file, this email message has this word in it or something. And here's an example on the bottom, actually, in terms of, it comes back with CPU usage as well. It says, if you think about the concept of the search, even in Microsoft, that search might take forever, or it might bog down system usage while it's going on. So, it's for you. Oh. Okay. Just in the recent versions of Microsoft have we got a built-in PK-zip that became part of the interface. But in other operating systems, this has been going on for years. We've always had tar. We've always had gzip as well, and a bunch of other RARs, other Zs, other utilities as well. So compression is kind of popular because it can take and make a smaller abstraction. You can take an entire source code build, tar it together, and then that way it's all in one place. And you can look inside the tar file, you can grep inside of the tar file. You can use it just as if it were a set of files. But when you're looking at it, it's one file. So a lot of source code is actually packaged in tars, distributed in tars. So when you're creating backups of files, transferring them to other hosts, files can be packed up in a larger file. So it's ease of manipulation, transfer speed, and file maintenance management. So that the tar is actually the predecessor to the zip file. And same concept of the zip file that I'm sure most of you are actually kind of familiar with. In the old days, it was tar actually came out of tape archive because we used to have backup tape drives. Looked like 8-track tapes. So, yeah, tape drives. So now the name's still there. We have, these are actually the equivalents that are supported on Windows these days. That for compressing files. gzip, gunzip, bzip, bunzip, very popular. I have something in my throat. Yeah, much better. I think it was a piece of Diet Coke. Piece of sugar. Actually, it wasn't sugar. There's no sugar in that. Alright, so using tar to create compressed files. In terms of compressed file types, nowadays everything's supported. In fact, you can get and unzip something. You can actually use a PK-zip on those as well, but those are popular compression utilities. Tar will create compressed files for you as well. When you untar it, you can specify a lot more options than you do in a Windows world. Now with a PK-zip, I've got loud in here again. You can unzip files, send them to different directories, have them nested certain ways in different hierarchies. You can do the same thing, but as command line switched. So you actually, this is actually pretty small, the CFC VFs. In this particular example, creates a compressed file, mytar.tar.gz, containing all of the files in a particular directory that's specified by the directory path. So it gets essentially it's the same utility that we're using these days in Windows, but it's a lot more feature rich. There's a lot more options to it. You can password protect it. You can do all sorts of different things to it. But if you think about it, a lot of the zip utilities, compression utilities are all patterned after each other. And at one point, where's the distinction between the different utilities? I mean, people swear by one because they think it creates smaller files or does a better job. Some actually make errors. If you think of the concept, it's taking and compressing and then it's expanding. There might be some inconsistency checks, perhaps, or there might be some problems. So, in terms of connecting to other machines, this is where the shell comes into place. We can also SSH for a secured shell, which is a lot of interesting thing because a lot of people download something called SSH client or SSH secure shell, and they perform what's called a telnet session, which is nothing more than a shell session through a secured channel, where the communication back and forth goes through an SSL or some other type of encryption or security mechanism or protocol that's applied. And the concept essentially with SSH is it's an encrypt remote login program. It's secure and it's trusted on non-secure networks. You haven't noticed the internet is not secure. And the internet's all Unix based, and you can get to Unix servers on the internet. If you use what's called a secure shell, you have an added level of protection, which means the packets that are being transferred back and forth might be a little slower in terms of the communication, but they're more secure. There's less likelihood of the packets being sniffed or stolen or translated or manipulated of some sort. And the security is a level of encryption that's added. So your receiving packets are unencrypted at your local shell. And when you send something, it's encrypted and then it's unencrypted at the host, essentially. And that type of security is preferred over other types because what you don't want to do is open up ports and have clients attached to the server in an unsecured fashion, because then you have, malware, you have a bunch of other stuff that could possibly cause problems to the server. So SSH or SS shell is actually kind of a common telnet program that's being used. If this was a huge university and we had student accounts into a Sun system, you would be using an SSH client to secure shell in. And if you're not familiar with this concept, we have two ways of secure shelling into a server. We can FTP, file transfer protocol, into it, or we can terminal into it. And the terminal is like that window I've been showing you when I've been exercising some of the commands. In the SSH shell, you establish a connection, you provide a user login password, and it creates a terminal window just the same way as it created a window when I went to terminal as a program on my local system. You have full Linux capabilities in terms of your login. So however your login script is defined, whatever you have access to. A lot of computer science students use this actually for programming language classes, for Unix classes, because you can write scripts, you can write programs, you can run programs, anything as if you were sitting at the university in front of the Linux terminal, Unix terminal. So it provides access to remote access, essentially. So let's see, copying files to the remote host. This is where you can actually use a FTP client, which is probably more common. You can also copy local to remote files and actually use the terminal window to copy files. So you can put something on a USB drive from your terminal window or back and forth, which some SSH clients actually disable because they want you to log in, but they don't want you to take something off or change something. So it depends on the access rights and what you've got exposed to. So you can copy a remote file from a remote computer to a local file by using R and L in front of the copy, in front of the sys command. It actually it gives you the ability to move files back and forth using a terminal session instead of an FTP program. Most people would just use an FTP program, to tell you the truth. So, Running commands on the remote hosts. You can actually run anything like from an SSH that you would normally do if you were at the host. In fact, when you connect to the host at the host, you're logging into a shell. When you're at the host, as an example of this computer, I bring up a shell window. I bring up a terminal window. It's the same terminal window I would get if I were at home, logged in from another computer connecting to this computer. So depends on, essentially, doesn't really matter where I'm sitting at, essentially. We have the environment that we have to look at. I think I showed you this command actually last time. env showed you the environment variables when I started looking at host and maybe it was host name or something, or user or something like that. So you can view all of the system variables and everything that's set. You can create one of your own if you wanted to. In fact, this is part of the shell scripting that I'm going to get into when I start talking about scripting languages. Some of the languages utilize, in fact, Perl is an excellent example. It's one of the oldest Unix scripting languages that uses environment variables. So you can see, how long has this user been logged in? Where is this user? What terminal is the user logged in from? How many files do they have open? What privileges does this user have? All a bunch of information essentially about the session, about the user, about anything that you're setting. In fact, you could write a program that creates an environment variable, adds it to your environment, and then sets a value. And it kind of sounds like a variable. So you can actually have variables essentially that sit around. And essentially you have a running program because you have that environment set, that login. And the session is your running program, and these environment variables are your variables that you're using. So it comes in very powerful, actually. It comes in useful for some scripts and things, which gives us the basic script concept. So when I talk about the kernel coming up next in the next lecture, I talk about scripts a lot because we have different types of scripts. The kernel itself runs a script. In fact, that's the first thing that happens. So you turn the computer on, and the brains of the operation, the kernel, wakes up, starts activating. And the first thing it's going to run it's called a startup script for the kernel. That's going to load this module, load that module. Finally, it loads other scripts on top of that script, and then eventually it'll load user-defined scripts, and then eventually it loads the shell. And the shell is the first user input to the system. So we talk about, in the next lecture, I'm going to talk about kernel mode and user mode. And usually you draw a diagram out. It's usually a square with a line down the center. You got the kernel on the bottom and you got the user on the top. And all the scripts end at the line coming upward, and then all the user level scripts run above the line. And it's just basically an abstraction to define the separation between what's called the user mode and the kernel mode. And it's nothing more than a bunch of scripts, long story short. Everything on Unix is a bunch of scripts. It's just a bunch of files running commands. And the whole abstraction is who owns the command, and who ran it, and why. And then what command is running what other command. It's actually kind of a basic system if you think about it, the concept. And it's kind of like what's happening in Windows. It's the same concept. We have some command.com that's starting, that's loading a DOS-based system that's loading a Windows desktop on top of it. It's all sequential in a hierarchy. If something fails, the whole system doesn't load, essentially. Same thing happens in Unix. Back to the basic script. Many times it's helpful to create a script. Essentially, a script is nothing more than a saved series of commands by concept. And instead of running each command individually, you run one file, and it runs everything for you. So it may aid in post-processing something, system administration, automatic mental tasks, backups. Backup scripts are very popular these days. Well, why are you going to sit there and run it manually? In fact, you can use a time scheduler and have it run at midnight in the background. And then you can go home, watch TV, and get paid for running system backups. Actually, it was interesting. A lot of people did that. And then people realized, oh, it's not that hard. Oh, what are we paying you for? You're not even there. Oh yeah, but I don't have to be there. I just tell it in, start the script if I don't have it on the scheduler. Or I can just tell it in after a late show and figure out did the script work correctly. Make sure everything's good, and then I can go to sleep. So we have a pound sign here. Basically at the text file level that's telling us what type of script. We have many different types of scripts, and I'll save all of the scripting details from when we start looking at them. I already talked about the variable concept, actually. In terms of environment variables, this is what it's referring to. And here's the slide showing you the convention. So by convention, system variables are capitalized, which is why if you type in env, you see a bunch of capital. Home, this is the directory where home is located, and path, all sorts of different other things that might be set. So a setting system variables differs by each shell, actually. And each shell can have its own set of variables. So you load up a bash shell might be different than a C shell. It might be different than another shell. And the shell actually runs a script. So when you log into the shell, we have a login script that runs and authenticates the user. And then we have an initialization script that initializes the environment, sets all the environment variables. So you can automatically set stuff ahead of time. These scripts actually provide the automation. There's plenty of seats up front. You want to sit up here? Okay. So user-defined variables and scripts are lowercase normally inside of the script when they're user-defined. If you just think, if you see something and it's at capital letters, it's most likely an environment variable. So if you think of it, you could possibly get tripped up in variable names. They do have the $sign next to them, but it might be hard to remember why something was said or where something came from. You're just using home all of a sudden. You're like, where did that come from? And then you know, well, it's capital, then that's going to be an environment variable. Lowercase is going to be user-defined in a script, because you can create your own variables in terms of your environment, and you can actually add them to the environment. You can pull them from the environment, which is different than, let's say, a Windows system normally. Windows system, you're stuck with your path environment variable normally. You can set a class path normally. Yeah, path is about it. And you don't really set variables like home, or you set username. Yeah, you can, actually. You can set some of them. But it does have limited capabilities. A little bit harder to do. You have to go through the control panel, I believe, with the system in order to set that. But I'm sure there's manual commands as well that still exist. Conditionals, you can use this in your scripts. These are in your text files. Normally when you see this stuff, it's like, oh, you're writing in a programming language. The interesting thing is it's one and the same. So writing the commands out of a Linux prompt is sort of like programming. That's why they call it systems programming. You're writing it at a system level, especially if you're using a C shell. You're actually using C commands that you're writing and running. And so there's no compiled program, there's just this command that you're running. It's going to printf something or scanf something, or it's going to do something in terms of the functionality. Conditionals is if a condition, then do something, then do something. It comes in handy, essentially, for writing scripts. I'm not going to go through a lot of stuff, but we have the same things that we'd normally have in a programming language, we have in a shell script environment. So performing loops is an example. For loops, do while, done, to say we're at the end of the loop. And each programming environment and each scripting language is going to have its own set of syntax and its own rules. And we're going to look in this class at Perl and at the C shell, which are the two that we're going to focus on. And I believe you have assignments on both of them, actually. So putting it all together, here's a script, example script that puts together some loops and some commands. And you kind of notice that there's no semicolons at the end of each line, and it's not quite as formal. You could save these in files and change mod on the file, make it executable, and run it just like an executable file, essentially. But it's all written in text. So a little bit more on my ls info. You can create different tricks and different things to kind of save yourself some work in the future. And create a script, let's say, is used to place out, the output of a command into a variable. So, in fact, you'll see a lot of Linux people, a lot of Linux admins creating utilities for themselves. And sometimes they'll put them in a special directory, and they'll share them with other system administrators. Like, this is what we do to clean out all the log files. This is what we do to clean out all the cache files or something. And you run the commands, and the commands are shared, and it pretty much automates the work, essentially, for everything. So the textbook for this course, it really isn't a required textbook, but it is one of the best books on the market if you're interested. It doesn't cover, it does cover, actually, kernels, and it does cover most of the lecture materials, actually. But I thought I'd mention this book here. Not bad. It's a very, very, very technical book. It's not a Unix for dummies. So It's definitely worth it as a reference. Nobody ever reads the book cover to cover. You would look up stuff in there and say, well, what is this Perl language? Or, what is this script used for or something? And it's a great reference. And the internet is also a great tool as well. So that was what we were supposed to have covered last week, but never got to because we were short on time. So this week, we are going to cover the Unix kernel, which is actually lecture 2. So we're progressing through the course at a slow pace, but we're getting there. Internals in terms of the motivation. Actually, every operating system out there on the market uses a kernel. And the kernel itself, the knowledge of the kernel, helps your understanding of building an operating system. And the interesting thing about Unix and Linux is you can make your own operating system by compiling your own kernel, essentially. And you've created a new breed, a new distro, and you've got your own operating system. It's the easiest way to create an operating system. Build your own kernel. And there's a user interface GUI tools called menu config and stuff to actually do this, which is kind of scary. However, getting them to work is the scarier part. Given enough tools, if you hit the right options, it might work. But you really need to know what you're doing in terms of the concept, in terms of what you're trying to build. So designing high-performance Unix applications may also help if you know something about the kernel itself. So what is the kernel? Good question. It's part of the operating system that contains code for, well, I would say the brains of the operation. But it's generally controlling the execution of processes, because it's starting the process concept. It's creating what's called a process table. It's way too loud in the back. So I stop talking until everybody else stops talking. Oh, much better. Okay. So it controls the execution of processes. It controls the process table. Most people describe, well, let me just scratch that. There's a couple of different ways of describing what a kernel is. Usually people describe it as a bunch of utilities. So what do we have? We have a file system support. We have the abstraction of the process and the process control block. We have I/O, input-output. We have external memory, internal memory. We have a bunch of utilities, and you start talking about an operating system. If you break it all down into functionality, the kernel's everything. The user mode is just the operating environments. It's just the rides above, which is why they usually draw the box with a line in the middle of it. And say there's really two different modes. There's the kernel mode, and then there's the user mode. The user mode is protected, which is what the original philosophy was. If we build an operating system that boots up, that gives the user a command prompt, and we can protect everything underneath it, then we can ensure that the operating system is stable and that everything that the user is doing is managed by the kernel. And we can create a stable working environment for which the user can create user-level programs and run programs on the system. So there really is a huge separation between what is called the kernel mode and what is called the user mode. A lot of it's for protection. It's a self-protecting kind of kernel. And we've got little kernels, we've got big kernels. We got different sizes. We have multiple kernel environments. We have mono kernels, single, multi-purpose kernels. And all of these different terms and techniques is basically describing what does the kernel actually do. What is it in charge of? So as an example, the single kernel, the entire operating system is one file. It's one massive, and the monokernels are usually big because they contain everything. So what's everything? Well, utilities, data structures, programs that the user is going to need to support the user mode, but drivers, hardware drivers, drivers for its startup, for its file support, for its device support, all encapsulated inside of the kernel. And then we have lightweight, itsy-bitsy, small footprint kernels that do nothing but load modules. So it's an itsy-bitsy little file, and all it does is load what's needed, and it does it usually just in time. So if you've got a small operating environment, an embedded system with 1 megabyte of RAM on it or something, right, just some flash memory, you're going to store a little bitsy kernel on there, It's going to load up a device that maybe has secondary storage on it. You're going to load in device drivers from that storage. You're going to grow it, and the whole system's going to boot out. The environment's going to be created from a bunch of different sources of memory, perhaps, from a different environment. Makes it feasible. Or we have the, slip the disk in, like what you're going to do with your bootable disk. And the kernel loads, the modules load, everything loads. That's 1 or 2 files on that disk, actually. That's a huge kernel that's loaded on a CD-ROM drive. That's preset. Everything's preset on it. So, in describing all of these different methods of creating kernels, the objective, or what I'm trying to do, is give you the impression that we're flexible. It's not like Windows. What do you do with a Windows disk? You install it. All Windows systems are the same. They all look and feel the same. All Unix systems are different, which is why you go online and you say download Linux. Well, what kind of Linux? You got Red Hat. You got many different varieties of Linux. We got small. I had you go to DSL, darn small Linux. It's itsy bitsy little kernel, doesn't load any drivers at all. Just loads the basic necessities. We got big kernels, little kernels. We got the Mac kernel, based on a BSD Linux version, Unix version actually. So the impression I'm trying to give you is that they're multi-purpose yet also specific towards different operating environments, different hardware, different software support, different needs. Not as generic as Microsoft Windows. And the kernel is the brains. That's the operating system that you're installing. So people like to build kernels because you can get a small footprint. Who cares about footprint size? Well, we care because it takes longer to load a bigger footprint. So it takes longer to load Windows. It will always take longer to load Windows because it supports everything in the world. If you only have one type of hard drive, you only have one type of keyboard, one type of mouse. If you build a kernel that has just the driver for each one of those suckers, then you got half, 3/4. It's a little bit of memory that's needed for that kernel because it doesn't need to know about everything in the world. Loads faster. So the goal of that was essentially in the beginning, we had multi-purpose big kernels, and then things got smaller. And so we built a kernel for a small embedded device, let's say. And then we changed the hardware. Oops, problem. Kernel doesn't work anymore. So then we have this thing called a monolithic, or we have is everything in there, or is just the basic necessity in there? And then we can add on drivers external to that. So we have this concept of kernel loadable modules. So now modern day Linux, when you download it, you get a single generic kernel that doesn't really have anything in it. And then all the modules are loaded by the kernel. The kernel goes out and says, hey look, we got an IDE port. Oh, load a driver for it. Oh look, we got this. Load a driver for that. And then we have kernels that we can actually build to load certain drivers. Then we have separation. So we have a multi-purpose-ish kind of kernel. And then we can update the drivers. And then we can update the system. And then we have a system that can evolve through time. So the entire history of this whole kernel has really evolved into something similar to Windows but more flexible. Because if you think about Windows, you can always update a driver. You can always change something, add support for something, which gives us flexibility. But it's huge. So modern day Linux, sort of mimicking that, but it's smaller footprint, loads faster, more customizable. Then we can build our own kernel, and we can just say what we have and not worry about it. And then we can say what we have and just say, hey, just load that driver, and then keep the driver outside. When I say outside, the kernel is compiled. It's a running program that's compiled, and it's written in a kernel language that's controlled by the build. So we run kernel build tools to configure the kernel, build the kernel, just like writing a software program, essentially. And most of it is done in C, actually. So you can go in, you can edit the kernel code, and you can create customizable configurations out of that. That is the difference between Red Hat, SUSE, GNU, Debian, all the different DSL, all the different varieties. People just went in and reconfigured, essentially, and rewrote the code. And that's custom kernel builds. And they all have their pros and cons. I like the DSL because it's small. It's darn small. So or damn small, depending upon how you're defining the terms. So let's see what other parts of the kernel code that I haven't mentioned. Allocating memory for executable programs, allocating secondary research, managing secondary memory, making efficient storage, retrieving user data, managing user data, handling peripherals, terminal windows, tape drives, disk drives, network drives, all sorts of different things. Characteristics, kernels that loaded into memory and runs until the system is turned off or crashes. Interesting concept. It's kind of like an endless loop or a state machine. The kernel loads up and it just sits there. And if the kernel dies for some reason, your system dies. It's that blue screen of death that comes up, I guess, in the Windows environment. Mostly written in C. Also some assembly language that makes it efficient for the driver level stuff. Written for different reasons. User programs make the kernel services, make use of kernel services through an interface. So then we have these things called interrupts, and we have system calls. So when you take a systems programming course, you're at a user mode on top of the kernel, and you're using what's called the system call interface, or system command interface, because we have kernel written in C with a bunch of C commands that were defined for it. Some of the C commands are add a process to the process table. And these are all utilities. These are all C low-level system calls that from the user mode give you the ability to call down to the kernel and tell the kernel to do something. In a Windows environment, all you can do is pretty much print a file, maybe go to a file print service, or maybe go to a service, add a service, remove a service. In a Linux environment, you can do low-level system calls to tell the kernel to reboot itself, to tell the kernel to kill a process, start a process, clean itself up, empty its log files, tell me who's logged on, all sorts of different utilities. And so the communication through the system call interface is a barrier of security that rides on top of the kernel that protects it. It protects it, makes it stable. So in order to get down into the kernel mode, we have to use the system calls. If we don't use the system calls, we can't communicate with the kernel at all. So it provides services transparently that are always around, that always exist in terms of some of the characteristics. We have what's called kernel subsystems. And I mentioned some of these already, but here's a more formal listing of them. We have a file system. And you kind of think about the concept of Microsoft Windows. There are these subsystems as well. There's a file system. It's usually a FAT32 or NTFS or something. In terms of a kernel, we have different types of file systems that can be supported, as I mentioned last week. We can load on many different types because the abstraction is not closely knit to the kernel. It's not built into the kernel. It's a module that we can load that we can support the Mac. We can support HSF plus file systems. We can support Windows file systems or old FAT32 systems or something. So the concept of it gives us, and what we're going to do in this course is as we go through, when I get done with the basics and what the kernel's all about, then we look at the subsystems. You know, what is the file system in terms of that? What is the process management system? The input-output system. And these are all the kernel modules, kernel components that all make it unique in terms of its whatever service that it's providing the user. So when we talk about file systems, that's a directory hierarchy. Files themselves, we're all kind of familiar with that as computer users, I would hope. Process management, some of us are familiar with that as well, especially if we've ever had to go in and kill programs that were running that were stalled or were having issues. We have signals, signal catching, signal handling, and if you're familiar with C or C++, well, it's mostly C. We look at signals in terms of driver support. If you write a device driver, it's not a bad idea to be familiar with operating systems and Unix, because then you're familiar with the concept of a signal and how to catch, how to handle it, and how to work with the signal handler, because that's what you're doing. If you think of the abstraction, we have hardware, and we have the kernel that sits on top of the hardware, and we have the user mode that sits on top of the kernel. The user mode never communicates with the hardware, because we got sandwiched in between, we got this thing called the kernel. The kernel communicates with the hardware, and gives you the software abstraction that you use in the because what kind of software works with hardware? There isn't any, which is why we always have to load an operating system. So if I buy a CD-ROM drive, and I buy a motherboard, and I buy a USB port, and I solder it all together, and I get the CD-ROM drive connected to the USB port that's connected to the motherboard, and I turn the power on, all the pieces are going to sit there and look at each other. Well, they probably won't. They'll just burn up or something because my soldering's not that good. But in essence, we need software, which is where the kernel comes in. It gives us that layer of abstraction that makes the hardware identifiable. So we have the old-fashioned device driver still being used. That's usually written in assembly language, normally. That goes down from a ones and zeros point of view to register level, identifies signals that are coming from the hardware. As an example, the CD-ROM drive, the door opens, generates a signal. It's a number. It's something that the hardware is electronically sending out a code. It says, my door's open, my door's shut. I'm reading, I'm writing. Every one of the things mechanically that can be done on that driver has a signal equivalence to it. The signal gets sent up to the kernel. The kernel can catch the signals, but what does it do with the signals? It just keeps track of them. So we write a device driver that takes the signals and says, oh, okay, your door's open, then shut the door. And says, well, if this happens, then do this. If that happens, then that's a device driver, if you think about it. It's communicating, it's giving the kernel instructions on how to communicate with this particular piece of hardware. And so we speak with the device driver from the user mode. We go down and we say, okay, open the door. That's where we get the system calls from. The system calls come through the system call interface that deal with the kernel. We speak to the kernel. Okay, hey kernel, let me speak to the CD-ROM drive. Okay, let me put you in touch. Here, we got them on the line, and we're talking now to the driver that's associated with that CD-ROM drive. And I say, open the door. And lo and behold, the CD-ROM drive opens up the door. And the user puts a disk in, and oh, door's shut. And the signal comes back up. Signal goes up. Sometimes in terms of what's considered an interrupt. Actually, signals and interrupts are very similar. I'll explain interrupts in a few minutes. But signals come up, it gets generated. Interrupts essentially come up this way. System calls go down this way. So we capture the information. If we're not capturing it, we can't do anything with it. And so from a hardware level, we call it an interrupt, because the interrupt is the lower level implementation of the signal. The signal is generated from the kernel that gives us a signal to the user mode. So it's kind of a hierarchy of information that we have to capture from physical events that are occurring with the hardware, that are being stored, that are being logged, that are being managed, that get eventually sent up to the user. And so the user knows, oh, we have an error. Oh, we have a disk that's not reading correctly. So if we talk about all of the different hardware on a computer, what are we looking at? Just the interface to the hardware. So people categorize the operating system as the kernel. It's the kernel going back to our lovely thing you've been staring at, the file system. What's the file system? Well, it's a secondary disk that has a driver. The driver says, look, these are the blocks, and loads the file allocation table when it boots up and becomes recognizable and says, look, for the first 10 blocks, we're going to call you a file or something. And there's this whole abstraction that's interpreted. And as it's interpreted, the higher level abstraction turns into what we're calling the file system. But somebody had to invent, the order in which the bytes were going to be read and the abstraction was going to be created, and then lo and behold, wow, we have a tree. We have a directory tree structure that's created, and all this stuff is happening at the kernel level. The kernel is responsible for all that stuff. So when we look at file systems, you think, file system, that's pretty easy. It's actually quite complicated in terms of the different techniques, and there's pros and cons to each one of these, which is why we have so many different file systems. If it was easy, we'd have one file system and it would be supported by every device out there. Right? We only have one file size, and we have capabilities that work universally without any problems. Same concept can apply to process management. So the process is, that's pretty easy, we just create a new process. Well, how are you going to schedule those processes? Well, we have a CPU scheduler. In fact, we have an entire lecture on CPU scheduling because that you get in an operating systems course as well. And because what ends up happening is you've got, different queues, different priorities, different types of processes that need to be scheduled. You have processes that are being created by the kernel. You have processes that are being created by the user. The processes have different priorities. For example, if you had to write something to the disk, should that be a higher priority than playing a CD, or something, You have to put, and then the kernel decides on essentially what priorities to place and what processes actually need to be performed and what orders should they be performed in. It does it right from the beginning all the way up until it creates its first shell in which the user can actually log in. So the kernel tells the user when they can log in, essentially. Input, output, and as you've seen with the directional operators, we have different types of input and output. It's all device-oriented. We have terminal windows. We have many different terminal sessions that are even part of what we would consider a terminal. We have remote logins, network types of communications, process-to-process I/O that happens. We have all sorts of different levels of I/O in terms of the processing. Inter-process communication, another thing you end up getting in terms of, if you take a systems programming course, you learn about all of the different historical issues with inter-process communication, deadlock, starvation, all of the different issues. We'll briefly tap upon that when we start getting into the kernel nitty-gritties. Most important, memory management. I want to know what command was entered in and what should we do. Because if you think about the concept, we're looking at a kernel that might be on, let's say, a microwave. We might have a kernel, and it has a button input. You press a button, it generates an interrupt. Sends a signal. The kernel says, "Whoa, somebody pressed my start button." Okay, what temperature am I set to? Okay, somebody set the temperature, and we have memory that's being managed in terms of this piece of memory belongs to this process. That piece of memory belongs to that process. And it's essentially nothing more than organizing. It's like this ringleader. So you're organizing what memory is labeled by what name, what address, and stuff like that. So addressing schemes, that's an abstraction of the operating system or the kernel. So System V, BSD have different implementations of the different subsystems. Actually, every Linux breed has a different implementation. So it's just basically talking to the kernel. So I can actually kind of go through this because I've already gave you the entire overview. So processes access kernel facilities through what I call the system call interface. We call systems system calls, which are write, read. If you take a C course, we have different levels of libraries. We have system call interfaces, and then we have higher level libraries that are written on the system call. They do nothing more than provide a higher level API for system calls. The system call is an example for reading and writing. They don't use buffered I/O. It's just read a bit, write a bit, read a bit, write a bit. And it can get kind of tiring, so you can create a stream out of that. Read a sentence, read a word, and then you can automate it a little bit more. So that's what the API, or Application Programming Interface concept, comes out of providing a higher level interface to system calls. Coming from the downward up, peripheral communication through the kernel, well, we have that hardware interrupt that comes up. And then we have the kernel that generates signals from those interrupts. So the kernel contains several different data structures, and they're needed to implement what's called the kernel services. Not the same as a service on a Windows system. Services on the Windows systems are generally user-initiated. Although if you look at them, some of them are Windows, owned by Windows. Which is kind of weird, because usually on a Unix system, you don't have access. You can't even view what the kernel is loaded in terms of a service. We have a process table, and I'll talk about the process table in a future lecture in a lot more detail. It contains entries for everything that's running on the system. So if you think about it, it's just the kernel is essentially an algorithm to orchestrate multi-processing and provide protection and provide services to the user. So, and the login is the main way of initiating any type of session or any type of communication. We have an open file table. It contains entries for any open files. Everything on the system is a file, and it's read to and written from as a file, which is kind of interesting. We always think of, when people think of files, you always think of like, a USB drive or something, or a hard drive with files on it. which we're trained to think about a file system. Everything has a file index number in Unix when we read and write to everything. So even the drivers, it's just like a file. So we write to a port, we read from a port. It's file I/O. And everything has an index number. Every device has got an identification, a file number associated with it. We open up the file and we assign it to a piece of memory and we create a pointer out of it, which is why it's actually not a bad idea to be familiar with pointers if you're going to write a kernel, because it's kind of the same concept as used. You have shared memory, and you can also have interprocess communication through pointers happening at the kernel level. So multiple processes can share the same memory on the system. If you think about the concept, it can actually create a lot of multitasking. So you can get essentially not too much hardware doing a lot. Because in the old days, hardware wasn't as fast, memory wasn't as big, and so we paid more attention. And Unix is from before the 8086's days of the pre-supercomputers that we have today. But we had very limited memory to work with very limited hard disk space. So the developing the kernel started from a minimalist kind of point of view and trying to make things run efficiently, which is actually kind of a good thing to be involved with. But as operating systems get bigger and bigger, memory gets bigger, processors get faster, we don't necessarily have to be focused in the same direction. So there's different motives, different developments. So let's see, we have the execution mode. So execution mode in kernel mode, and we also have user mode. This is what I was describing before. Like I say, you can abstractly think of a box. Take the box and cut it in half and call the bottom part the kernel mode, and call the top part the user mode. They're two distinct separate systems, which is kind of unique to Unix and Linux. We sort of have that in Windows, but it's not really. It's kind of a loosely interpreted. So when a process is executed by a system call, the execution mode of the process changes from user mode to system mode. We actually have a switch where one user takes over, like the user is saying, hey, kernel, open up the CD-ROM drive. All execution stops up here in user mode, and the kernel says, oh, open a CD-ROM drive. Okay, go talk to that driver and open up the CD-ROM drive. And then we have this handoff. So not all the work is actually being done in user mode, which you might argue and say, well, that makes Unix faster. You think about the concept. The closer you get to the hardware, the faster things run. So if you're out there in user mode and you're going to run the command, it's easier to tell the other guy, call up the guy closer and say, hey, you run the command. You're going to run faster. You have a lot more resources allocated to you. So there's a switch. The modes switch back and forth. So essentially it creates efficiency because the user's not trying to go down and grab the kernel's arm and take the arm and go over here, and it's not trying to direct the kernel's directing itself, which is different than the Windows environment. In Windows environment, the user's directing the XP or the Windows kernel, if you want to call it a kernel, to do something, and you're doing it all from user mode. You're doing all the work. Your programs that you're writing are opening up a screen. They're opening up a file. They're managing the file. They're doing everything, and it's at a higher level, way far away from the hardware. So a Unix program will run faster. This is why people always argue for years that the Mac systems are faster than the Windows systems because it's on a Unix BSD foundation. So we have a switch that goes on between kernel and user mode, which means you have faster processing speeds of hardware-related things. So it is right. If you load up and test the internet access will run faster on a MacBook than it will ever on a Windows system because the kernel is responsible for that, and the kernel is running it at a low level, and it has reserved resources for that, and it takes higher priority. So your Facebook program or your web browser is not eating up all the memory; it just gets shut off temporarily. So you have different. In fact, you can notice the differences when you load the operating systems. That there's just different feel that goes on. It's because of the style of how the kernel is working and how the communication is working between your system. Alright, so we have a switching that goes back and forth. Processes in user mode can access their own instructions and the data, not kernel instructions and not data structures from the kernel. So user mode can't really access anything from kernel. It can just basically say run the system call, and vice versa. So the communication goes back and forth through an interface, the system call interface. And in kernel mode, the processes can access system data structures such as the process table and things that are related to the kernel. So the flow of control during a system call, and I think I'm trying to think here, probably got another 15 minutes or so. I'll find a good stopping point. So the user invokes a system call, for example, open a file, and it's the same file, same call, depending upon what it is you're opening. You're just going to open something. Every system call is allocated a code number, and so it says, oh, we got a number 95. So we have a log and a table that says user bhacker initiated a 95 code. Oh, it's an open, and then it has a lower level instruction that's associated with that. And it prioritizes its execution of its requests. So it has its own queue. It has its own information and its own instructions. So as an example down here, the C runtime library version of the system call replaces the system call parameters. So we have a wrapper that goes on top. Let's say we ran this open command through a program that we wrote in C, and we used fstream or something to open something, or fopen, file open, or something like that. So the code number into the machine registers and then executes what's called a trap, which is a machine instruction, which is essentially a software level interrupt. It's a trap. So it says, create an interrupt that's generated to provide an open facility on this hardware. And then we have this communication that just goes back and forth in terms of the instruction set. So the trap instruction, and this is essentially more vocabulary for you, uses the system call number as an index into the system call vector table. It's actually, most people don't like the word vector, so they take it out and they say, well, what's a table? It's a table. It may not necessarily be implemented using a vector data structure, maybe. So system call table. So we have it loaded in the memory, and so we have pointers. We have an array of pointers to kernel code for each one of the system calls. For those people who don't like pointers, you're never going to be a Unix. You're never going to build your own kernel, probably. I don't know. It's all pointer based. Because think of the concept. You can just throw stuff out into memory and keep track of the memory locations. And the kernel doesn't have that much memory associated with it. And you don't want to give the kernel that much memory because you got to save it for user mode. So most people wonder, well, I have 2 megabytes of RAM or 2 gigabytes of RAM on my system, but my Windows system only sees 1.5 gigabytes or something. It's because the memory is reserved for kernel usage. So what are they using it for? Well, they're using pointers. They're taking and saying, this is the information that we're storing our process control block in. Right here. This is the address. This is the address we're storing our CPU scheduler in our CPU table, and this is our system call interface. And this is all of the different tables, all the different data structures are all stored in memory. It just goes in the memory location and reads and writes it and uses it in terms of the hardware abstraction. Uses the information to essentially organize everything it needs to keep track of. Otherwise, you don't want it sitting around in memory. You don't want it like buffered. If you don't use pointers, the system runs way too slowly. It speeds up the operation. Alright, so code corresponding to the system call executes in the kernel mode, modifying the kernel data structure if necessary. If not, modifying the instruction, modifying maybe perhaps what's stored at the memory address, performs a special return instruction that flips back into user mode and returns. This is where people who don't like C again, we have function calls with returns. This is the concept of the return is from Unix, because Unix is this first C language or B language that was actually created. And it's nothing more than a programming language interface. So we send a call, it's a function call, it's a system call to a kernel. Kernel returns a value, and the return value is coming back. So you gotta like C if you're gonna get into this. You gotta like pointers, because it's all part of memory management, mallocs and stuff, because that's all the data structures are using in terms of the system call interface. So synchronous versus asynchronous processing. Usually processes performing system calls cannot be preempted. If you think of the concept, if you're writing something to a disk, you're physically writing something. Do you really want to stop that? And there's no buffered memory. It's taking from a pointer location writing it to a byte on a secondary storage using a driver to say, here's this location, this location. If you want to interrupt that, you're going to lose your memory. So essentially what ends up happening is the kernel gets processing priority time. And everything is not in the, and another vocabulary word for you is we talk about preemptive, non-preemptive, and preemptive processes. Kernel mode are not preemptive. User mode, preemptive. It can be interrupted. So we have, most users don't even notice it, but there's slight delays where no processing happens. The system just sits there. Usually on a command line interface, you notice it more. When you type in a command and you wait a little bit longer than you did the last time you typed in that command, or the results come back a little bit slower or faster. It's because you're being stopped. So processes must relinquish voluntarily the CPU from an example, from waiting for I/O to complete. I/O will always be non-preemptive, and it will always take higher priority over everything else because there's more room for errors. So CPU using I/O, that's where you get dual processors support. So here's an interesting example for you. You're building an embedded system and you're going to load a Unix kernel. You're going to utilize CPU usage. So you're going to put on a dual processor, or multiple CPUs, so you can essentially get more processing done quickly. Because what ends up happening is the reading and the writing will make the user interface extremely unusable. The user is going to sit there. You have an MP3 player. You have an iPod as an example, and you're going to press play. You're going to sit there and wait 5 minutes? No, you have to have a strong processor. So some of the decisions in terms of the hardware that goes into these little devices are very process-oriented, because especially if they're doing reading and writing, because you need faster processing for that type of computation because you can't interrupt it. Otherwise you get parts of the song, bits of the song, and you stand the chance of making the interface unusable. So there's different interface design techniques that kind of compensate for some of it. So sometimes you hear like noises, you're like, say, where's that coming from? And there's just white noise because you have to wait because the I/O is not done yet. Or it says, please wait, loading, please wait, please wait. Every one of these devices you'll see loading, please wait. Even on the phones you see, the droid thing comes up. Well, it's because the kernel's booting. Can't stop the kernel. Or it sits there and kind of, you see some symbol comes out on the screen or something happens because the kernel is doing something. It's a kernel-based system. The Droid application platform is kernel-based. It's Linux-based. So it's doing some I/O of some sort. So because the user mode is going to come to a complete dead stop, and the kernel is going to take over 100%. And it only happens with I/O. Other processing works just fine. So the scheduler does not allocate sleeping processes any CPU time as well, because you might have something open but you're not using it. It's dead, it's sleeping, so why waste space on it? So hardware devices is servicing the I/O request. It's going to service the I/O request. So I think I'm going to end actually after interrupts and exceptions. Let's see, process execution interrupts. It's a long ways. Oh yeah, 3 slides. It's not that long. It's a good point to stop actually. I was looking for a good breaking point. Interrupts and exceptions. I talked about interrupts. What's an exception? We have I/O exceptions. Those are errors, just like interrupts. It just says error code, error code. And if we have good exception handler, well, in terms of our driver, we can set up a disk full instead of a 99955 whatever that came up out of it, or bad block, or something that's more user friendly. So Unix systems allows devices such as I/O peripherals and clocks to interrupt CPU asynchronously, which means we're keeping track of stuff that's going on simultaneously, but we're doing it asynchronously. If you think of the concept, kernel is out there listening to all of the hardware, and let's just call them ITU students, and you get 5 of them yelling at you, I need a grade change, I need a grade, or can I add your class, can I add your class? Is the kernel going to listen to all those 5 people simultaneously? No. So instead it's going to take a number. No, it's going to, okay, here's a piece of paper, write down all your requests, and keep track of them, and then asynchronously go back and deal with them, which is essentially how you come up with a data structure to capture all of the interrupts that are going on. So one recipient of the interrupt kernel saves its current state, So it's context. This is why sometimes they call it context switching between processes. Frozen image of what the process was doing determines the cause of the interrupt and services the interrupt. And the interrupts could be good, they could be bad. They could be producing errors, they could be producing results. So the devices are allocated interrupt priority based upon the relative importance. Hard drives normally have a higher priority. CPU will have a higher priority. Critical components of the system. Your thumb drive, excuse me, your USB drive is not going to have a priority. It's going to be the last thing that the interrupt's going to listen to, that the kernel's going to listen to. And then the kernel services interrupt. It blocks out lower priority interrupts, but services higher priority interrupts first. So we have process execution levels, and this is just an example of your typical high versus low priorities. As I mentioned before, machine errors are pretty high. Typical interrupt levels, so sometimes prevents the occurrence of interrupts during critical activities to avoid corruption of data. So it won't actually service an interrupt if something's going on in terms of I/O or something of that nature. Machine errors, clock errors, high priority disk errors, networking errors, terminals. Software interrupts are pretty low. User's program failed, who cares? So here's our definition. Interrupts. Serviced by kernel interrupt handlers. This is the same concept we get when we're writing a C program. We write a handler to catch. We try and catch. Must be very fast to avoid losing any of the interrupts as well. We have a handler in most Unix kernels, put it in a table. So you have a data structure that keeps track of the interrupts, and everything's captured. And then you can go back to the table and process everything in order if you wanted to. So an interrupt of a higher priority occurs while a lower interrupt is being serviced. Nesting will occur. Higher interrupt will be serviced. The lower ones will be sitting in a queue waiting to be serviced next. Alright, I think I'm going to stop because I'm hitting a good point to stop actually. Otherwise I get system overload. So yeah, INOs are fun. We'll talk about, so next week we'll talk about disk architecture. Somebody remind me, we stopped on slide number 15. So the good students in the front row here. 15 is, well, let's talk about disk architectures, file subsystems, INOs. Those are important. And the layout of the file systems, naming algorithms, mounting hard drives, and stuff like that. That's going to be, yeah, this is like a 60 or so odd slide lecture. So that will be the theme for next week. Will be file system support. Okay, we're done. Have a good, good warm week, I think.